In the summer of 1977, NASA launched two spacecraft that were designed to last 5 years. That's worth sitting with for a moment. 5 years. The engineers who built Voyager 1 and Voyager 2 designed them to survive long enough to photograph Jupiter and Saturn, collect whatever data they could, and then go quiet. Nobody was seriously planning for anything beyond that. The power would run out, the instruments would fail, and the mission would be over. That was the expectation. That was the plan. Neither spacecraft got the memo. As of 2024, both probes are still operating. Both are still transmitting. And both have traveled so far beyond the original mission boundaries that they've crossed into interstellar space, the region between stars, outside the sun's influence entirely, a place no human-made object had ever reached before. Voyager 1 is currently more than 15 billion miles from Earth. Voyager 2 isn't far behind. They are, by an enormous margin, the most distant objects humanity has ever built. And they're still talking to us, faint signals taking more than 22 hours to make the one-way trip home. Think about what that actually means. A spacecraft assembled in the early 1970s running on technology that predates personal computers is sending back scientific data from beyond the solar system. The people who built it are now in their 70s and 80s. Some of them have died, and the machines they built are still out there, still working, still crossing ground that nothing from Earth had ever crossed before. The story of how this happened starts with the stroke of timing that the solar system offers only once every 176 years. In the late 1960s, a graduate student at Caltech named Gary Flandreau noticed something remarkable while working on a trajectory study for NASA. The outer planets, Jupiter, Saturn, Uranus, and Neptune, were falling into an alignment that would make it possible to visit all 4 of them on a single mission, using each planet's gravity to slingshot a spacecraft toward the next one. This kind of multi-planet alignment happens rarely. The window Flandreau identified was opening in 1977. After that, it wouldn't come around again until the 2015s. If NASA wanted to take advantage of it, they had roughly a decade to build the spacecraft and get it off the ground. That's a tight margin. And the mission they designed around that window was, by any reasonable standard, audacious. 2 spacecraft would launch within weeks of each other. They'd fly past Jupiter, use its gravity to bend toward Saturn, and from there the trajectories would diverge. Voyager 1 heading for a close pass of Saturn's moon Titan. Voyager 2 continuing on toward Uranus and Neptune. The instruments aboard were built for planetary science. The design life was 5 years. The expectation was that the mission would end somewhere around Saturn. What actually happened was something else entirely. Voyager 1 reached Jupiter in March 1979. What it found there was already surprising. Active volcanoes on Io, a moon scientists had assumed would be geologically dead and frozen. It wasn't. It was the most volcanically active body in the solar system. Nobody had predicted that. By the time Voyager 1 reached Saturn in 1980, the discoveries were piling up faster than the models could absorb them. Saturn's rings turned out to be far more complicated than anyone had expected. New moons appeared. Strange structures showed up in the ring system that required entirely new physics to explain. By then, it was becoming obvious that shutting these spacecraft down would be a waste. The instruments were still working, the power was still flowing, and both probes were heading outward, away from the sun, toward a region of the solar system that nobody had ever directly explored. NASA extended the mission, and then extended it again. Voyager 2's trajectory took it past Uranus in 1986 and Neptune in 1989, making it the only spacecraft in history to visit either planet up close. Everything it found there was unexpected. Uranus was tilted on its side. Neptune's winds were clocking speeds that nobody had predicted. Triton, Neptune's largest moon, had geysers. Active geysers, shooting nitrogen gas into space. Every encounter produced surprises. Every flyby forced a revision. And then the planetary phase ended, and both spacecraft kept going. They kept moving outward, crossing the outer reaches of the solar system, heading for a boundary that scientists had long theorized about but never been able to directly measure. The edge of the sun's protective bubble, where the solar wind finally gives out and interstellar space begins. The instruments were old. The power was slowly fading. About 4 watts lost every year from the nuclear generators that kept the spacecraft alive. The engineering team at JPL had to make increasingly difficult choices about which systems to shut down and which to keep running. There was no room for error. There was no backup mission if something failed. There was just 2 elderly spacecraft crossing the longest stretch of empty space any human-made object had ever attempted. Voyager 1 crossed into interstellar space in 2012. Voyager 2 followed in 2018. And what they found out there, at the very edge of the sun's reach and beyond it, turned out to be stranger than almost anyone had predicted. The reason 2 spacecraft could fly past all 4 outer planets on a single mission comes down to geometry, and that geometry only cooperates once every 176 years. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are each moving in their own orbits at their own speeds. Most of the time, they're scattered around the solar system with no useful relationship to each other. Getting from one to the next requires enormous amounts of fuel and time. But every 176 years or so, the geometry lines up in a way that changes everything. The planets arrange themselves in a rough arc, and if you launch a spacecraft at exactly the right moment and angle it precisely, you can use each planet's gravity to slingshot toward the next one. You steal a little of each planet's orbital energy and convert it into speed. No extra fuel required. The planet barely notices. The spacecraft accelerates dramatically. And instead of 1 planetary flyby, you get 4. This technique is called a gravity assist. And without it, the Voyager missions as we know them simply don't exist. A direct flight to Neptune without gravity assists would have taken decades longer and required fuel loads that weren't remotely practical. The alignment window that opened in the late 1970s made the whole thing economical. Miss that window, and you wait another 176 years. NASA didn't miss it. Voyager 2 launched on August 20, 1977. Voyager 1 launched 16 days later on September 5th. Despite the names, Voyager 1 was actually on a faster trajectory and pulled ahead. Both spacecraft were aimed at Jupiter first. That was the entry point for the whole sequence. Voyager 1 reached Jupiter in March 1979. What it found there was already more than anyone expected. The Great Red Spot turned out to be a storm system of staggering complexity. Jupiter's magnetic field was enormous, far larger than theoretical models had suggested. The moon Europa showed a cracked, icy surface that hinted at liquid water underneath. And then there was Io. But that discovery deserves its own full explanation, and it's coming. The point is that Voyager 1's Jupiter encounter alone would have justified the mission. Voyager 2 arrived at Jupiter 4 months later, in July 1979, and confirmed and extended what the first probe had found. Between the two spacecraft, scientists got a detailed picture of a planetary system that turned out to be far more dynamic and complicated than anyone had modeled. Then both probes used Jupiter's gravity to accelerate toward Saturn. Voyager 1 reached Saturn in November 1980. The rings, which astronomers had observed through telescopes for centuries, turned out to have structure that nobody anticipated. There were gaps and waves and braided patterns and thin ringlets woven together in ways that required new physics to explain. Voyager 1 also made a close pass at Saturn's moon Titan, which has a thick nitrogen atmosphere, the only moon in the solar system known to have one. That close pass at Titan bent Voyager 1's trajectory out of the plane of the solar system entirely, which meant it could no longer reach Uranus or Neptune. Voyager 1's planetary tour was finished. It was heading outward, above the ecliptic, into the long dark. That left everything to Voyager 2. Voyager 2 reached Saturn in August 1981. It completed its own pass through the ring system, confirmed several of Voyager 1's findings, and discovered additional detail. Then it used Saturn's gravity to bend toward Uranus. At this point, the original mission was technically complete. Both spacecraft had done what they were designed to do. The instruments had lasted longer than planned. The data was coming back clean. A reasonable organization might have declared victory and shifted resources elsewhere. Instead, a group of scientists and engineers at JPL made the case for extending the mission. Keep Voyager 2 on course for Uranus. Then, Neptune. The spacecraft was healthy. The trajectory worked. The opportunity would not come again for 176 years. NASA agreed. It was a relatively quiet decision at the time. It turned out to be one of the most consequential calls in the history of space exploration. Voyager 2 reached Uranus in January 1986. It's still the only spacecraft that ever has. Uranus is tilted on its side. Its rotational axis sits at nearly 98 degrees relative to its orbit, meaning the planet essentially rolls around the Sun rather than spinning upright. Nobody fully understood why before Voyager, and the leading explanation now involves a massive ancient collision. Voyager 2 discovered 10 previously unknown moons and found that Uranus has a magnetic field that's tilted and off-center in a way that remains difficult to fully explain. It was a strange, cold world with almost no detectable internal heat, which made it an outlier among the gas giants. Scientists expected it to behave like Jupiter and Saturn scaled down. It didn't. Then Voyager 2 flew on toward Neptune. It arrived in August 1989, 12 years after launch. Neptune's atmosphere produced the fastest winds recorded anywhere in the solar system, up to 1,500 miles per hour. The planet had a storm system, the Great Dark Spot, that bore an eerie resemblance to Jupiter's Great Red Spot. Voyager 2 discovered 6 new moons at Neptune and found that the largest, Triton, was orbiting the planet in the wrong direction, retrograde against Neptune's rotation, which meant it was almost certainly a captured object rather than something that formed there. Triton also had geysers shooting nitrogen gas several miles into the sky. A moon at the edge of the solar system, in temperatures cold enough to freeze nitrogen solid, somehow still geologically active. Think about what had actually happened across those 12 years. 4 planets, dozens of moons, ring systems of unexpected complexity, active geological processes where scientists expected frozen inertia, magnetic fields that didn't match the models, weather systems that defied easy explanation. All of it returned by 2 spacecraft that were designed to last 5 years. And all of it had been accomplished before the spacecraft reached the part of the journey that would eventually matter most. The long coast outward, past the edge of everything familiar, toward a boundary nobody had ever directly measured. By the time Voyager 2 finished its Neptune flyby in 1989, the mission had already exceeded every reasonable expectation, and it was only just getting started. Before Voyager 1 reached Jupiter, the assumption was straightforward. Moons that far from the sun would be cold, geologically dead, about as interesting as gravel. This wasn't an unreasonable position. The logic made sense at the time. The sun's energy drops off rapidly with distance. By the time you reach Jupiter, more than 5 times farther from the sun than Earth, the amount of solar radiation hitting a surface is roughly 25 times weaker than what we receive here. Geologic activity, as far as anyone understood it, required heat. Heat came from either a nearby star or leftover warmth from a planet's formation. For a small moon orbiting Jupiter, neither source seemed sufficient. The scientific community expected cold, cratered surfaces, dead rock, ancient impact scars, and nothing else. Then Voyager 1 flew past Io on March 5, 1979. One of the navigation engineers, Linda Morabito, spotted something in the imagery that didn't belong. A plume, rising hundreds of miles above Io's surface. It wasn't a smear on the lens or a processing artifact. It was a volcanic eruption actively in progress, captured in a photograph taken from a spacecraft flying through the Jovian system at tens of thousands of miles per hour. The team looked more carefully. There wasn't just one eruption. There were 8 active volcanic plumes visible in the Voyager images. 8. On a moon that was supposed to be geologically inert. Think about that for a second. Scientists had been studying Io through telescopes for decades. Nothing in any of that observational data had suggested this was possible. The discovery didn't just revise the models, it demolished them. What makes Io volcanic isn't solar energy or residual formation heat. The mechanism is something called tidal heating, and it's both elegant and brutal. Io orbits Jupiter in a gravitational relationship with 2 other large moons, Europa and Ganymede. The orbital resonance between these 3 moons means Io is constantly being pulled in slightly different directions as it goes around Jupiter. Jupiter's gravity is immense. The planet is more than 300 times the mass of Earth, and as Io orbits, Jupiter's tidal forces flex and squeeze the moon's interior the way you might knead a ball of dough. That flexing generates friction. Friction generates heat. And that heat, trapped inside Io with nowhere to go, drives volcanic activity on a scale that makes anything on Earth look restrained. Io loses about 1 trillion watts of heat through its surface. That's the energy output of roughly 1 million nuclear power plants, radiating continuously from a moon that's only slightly larger than our own. The result is a surface that gets completely resurfaced by volcanic material every few million years. There are essentially no impact craters on Io. Any crater that forms gets buried or erased almost immediately. The surface is so geologically active that it's essentially new. What Io looks like up close is genuinely alien. The surface is covered in sulfur and sulfur dioxide frost. That gives it a palette that runs from yellow and orange to red and white, with patches of black where fresh lava has recently cooled. Some regions are flat volcanic plains. Others are dominated by mountains, not volcanic shields like Hawaii, but tectonic structures pushed upward by compression, some of them taller than anything on Earth. The tallest peak on Io, Bo Sole Montes, rises to about 59,000 feet. That's higher than Mount Everest by nearly 20,000 feet. The volcanic plumes themselves reach extraordinary heights. The largest ones, driven by eruptions of sulfur dioxide gas, can extend more than 300 miles above the surface. In Io's weak gravity, and with essentially no atmosphere to slow them down, those plumes arc upward and then fall back down in a perfect ballistic arc, depositing material in huge circular patterns across the surrounding landscape. From above, those deposits look like rings or bullseyes, and Voyager captured several of them in striking detail. The temperatures inside the active volcanic features are extreme. Lava flows on Io reach temperatures above 3,000 degrees Fahrenheit in some cases, hotter than any known lava on Earth. Hotter than most lavas in the geologic record. The surface sits in a near vacuum with atmospheric pressure so low it barely counts as an atmosphere. Radiation from Jupiter's magnetosphere bombards the surface constantly. Any unprotected object left on Io would be simultaneously irradiated, chemically eroded by sulfur compounds, potentially buried by ongoing eruptions. It is, by any useful measure, one of the most hostile surfaces in the solar system. The implications extended well beyond Io itself. If a moon the size of Io could sustain this level of geological activity through tidal heating alone, that meant other moons, in other orbital resonances around other giant planets, might be doing something similar. Europa, which orbits Jupiter just outside Io, turned out to have a global liquid water ocean beneath its icy shell, also kept liquid by tidal heating. The idea that tidal forces could power not just volcanism but potentially habitable conditions in the outer solar system was a direct consequence of what Voyager found at Io. That single discovery opened an entirely new branch of planetary science and reshaped the way researchers think about where in the solar system life might be possible. Before the Voyager flyby, the outer solar system was a collection of frozen, quiet worlds sitting in the dark far from the sun. After Io, it became something fundamentally different, a place where the physics of gravity alone could drive geological processes violent enough to reshape entire surfaces, produce mountains taller than any on Earth, launch material hundreds of miles into space. It was the first time anyone had watched a volcano erupt on another world. It made clear that the solar system was a much more violent and alive place than the textbooks had described. Saturn was supposed to be the mission's showpiece, the planet with the beautiful rings that everyone expected to understand reasonably well by the time Voyager arrived. Scientists had been studying those rings through telescopes for more than 3 centuries. They'd mapped them, categorized them, and built models to explain why they looked the way they did. The assumption going in was that Saturn would be spectacular, sure, but it wouldn't be surprising. They thought they knew what they were going to find. They were wrong about that in almost every direction. When Voyager 1 reached Saturn in November 1980, the first thing the instruments made clear was that the ring system was far more complicated than the models had ever suggested. From Earth, you can see a few broad bands separated by gaps. Voyager found hundreds of distinct ringlets, braided structures, wave patterns, sharp edges that had no business being as sharp as they were. The rings were doing things that gravity alone shouldn't have been able to produce. Material in those rings should have spread out and blurred over time. Instead, some rings were narrow, well-defined, and almost geometrically crisp. The question was why? The answer turned out to be something nobody had specifically predicted before the flyby. Certain rings, it emerged, were being kept in line by small moons orbiting just inside and just outside them. If a particle drifted outward from the ring, the outer moon's gravity would nudge it back. If it drifted inward, the inner moon would push it out again. These moons were essentially acting as gravitational fences. Scientists called them shepherd moons. Once the concept was understood, it reframed how planetary rings could work anywhere in the solar system. Voyager 1 found the first confirmed example of this in Saturn's F ring, a narrow, kinked band with two small moons flanking it on either side. Prometheus and Pandora, they were named. They've since become among the most studied objects in the outer solar system. Think about what this meant. Scientists had a 300-year head start studying Saturn's rings. A mechanism as fundamental as gravitational shepherding had gone completely undetected until a spacecraft flew through and looked closely. It's one thing to say the solar system was more complex than expected. It's another to realize that the complexity was hiding in plain sight, in the most observed planet beyond the inner solar system, for centuries. Voyager 1 also discovered 5 new moons during its Saturn encounter. Voyager 2 followed in August 1981 and found more. By the time both flybys were complete, the known moon count for Saturn had jumped substantially. Some of these moons were small and irregular, captured objects with eccentric orbits. Others were embedded within the ring system itself, clearing gaps in the rings through their gravitational influence. The Encke Gap, for instance, was found to have a small moon called Pan sweeping a path through the ring material as it orbited. Every new moon raised more questions about how the Saturn system had formed and how it had maintained its structure over billions of years. But the rings and the moons weren't the strangest thing Voyager found at Saturn. Not even close. Voyager 1 turned its instruments toward Saturn's North Pole. What it detected there was something that looked at first like a data error. There was a hexagon. Not a rough hexagonal shape or a loosely six-sided pattern, an actual persistent geometric hexagon. A six-sided jet stream circling the North Pole with sides nearly as wide as Earth's diameter. Each side of the hexagon stretched roughly 8,700 miles. The storm system inside it was rotating. The whole structure was stable in a way that atmospheric systems simply aren't supposed to be stable, especially on a gas giant where winds can exceed 1,000 miles per hour and weather patterns typically shear apart and reform constantly. Scientists had no immediate explanation for it. The leading theories involve resonance between the jet stream and wave patterns in Saturn's atmosphere, a kind of standing wave locked into a six-sided shape by the planet's rotation rate and internal dynamics. The math can produce hexagons under the right conditions in a lab, but reproducing the exact conditions on a planet as massive and complex as Saturn, with a feature that large and that persistent, is a different problem entirely. Researchers are still working on it. Here's what makes the hexagon especially strange. It was there when Voyager flew past in 1980. It was still there when the Cassini spacecraft arrived at Saturn in 2004, 2.5 decades later. It's still there today. Weather systems on Earth last days or weeks. Major storm systems on other planets can last longer, but they evolve, change shape, drift in latitude. Saturn's hexagon just keeps going. The same six-sided structure at roughly the same size, holding together through decades of observation by multiple spacecraft and ground-based telescopes. Nothing else in the solar system behaves like it. The pattern from the Voyager mission was becoming very clear by the time the Saturn encounter ended. Jupiter had produced volcanic moons and radiation belts far more intense than anyone had modeled. Saturn had produced a ring system of Baroque complexity, a gravitational shepherding mechanism nobody had directly confirmed before, a collection of new moons, a geometric atmospheric feature that broke every intuition planetary scientist had about how gas giant weather was supposed to work. Each encounter wasn't just adding data, it was forcing a fundamental revision of the underlying models. The solar system, it kept turning out, was under no obligation to match the predictions built from the ground. The hexagonal storm is still there today, still spinning, still refusing to behave like anything scientists have a complete explanation for. Uranus and Neptune have each been visited exactly once by a spacecraft from Earth. That spacecraft was Voyager 2. That's not a historical footnote. That's the current state of things. No mission has been sent back. No follow-up probe is en route. Everything humanity knows about these two planets at close range comes from a single spacecraft that flew past each of them at tens of thousands of miles per hour, snapped what data it could, and kept moving. Voyager 2 reached Uranus in January 1986 and Neptune in August 1989. Those flybys lasted hours, and in those hours, we got the only direct measurements we have ever taken of two of the four largest planets in our solar system. Before Voyager 2 arrived at Uranus, scientists had a reasonable working picture of what to expect: a gas-rich world, some moons, a magnetic field of some kind. What they were not expecting was a planet that appears to have been knocked completely sideways at some point in the distant past. Uranus rotates at an axial tilt of about 98 degrees. That means it's essentially rolling around the Sun on its side. Its poles point roughly toward the Sun rather than perpendicular to the orbital plane the way every other planets do. Earth's tilt is about 23 degrees, Saturn's is 27, Uranus is at 98. That's not a variation, that's a completely different orientation. The most widely accepted explanation is a collision. Early in the solar system's history, something very large, possibly an object the size of Earth or larger, struck Uranus with enough force to tip the planet over and leave it in its current orientation. Think about what that impact would have looked like. A protoplanetary body, billions of tons of rock and ice, traveling at tens of thousands of miles per hour, slamming into a planet and transferring enough angular momentum to rotate it nearly 90 degrees relative to its orbit. The energy involved is almost impossible to picture, and yet the evidence that something like that happened is written into the planet's orientation every time you look at it. Voyager 2 also found that Uranus has a ring system, not as dramatic as Saturn's, but real and structured. It found 10 new moons during the flyby, bringing the known total at the time to 15. And it measured a magnetic field that is bizarrely offset from the planet's rotational axis, tilted about 60 degrees away from the poles and displaced from the planet's center. Nobody fully understands why. It's another aspect of Uranus that sits outside the normal models and hasn't been explained to anyone's complete satisfaction in the decades since. Neptune was the final planetary target. By the time Voyager 2 arrived in 1989, the spacecraft had been in space for 12 years. The engineering team had gotten very good at coaxing precise maneuvers out of aging hardware. They needed every bit of that skill because Neptune presented its own set of surprises. The most immediate was the wind speed. Neptune has the fastest winds recorded anywhere in the solar system, reaching about 1,500 miles per hour. To put that in some context, the most powerful hurricanes on Earth produce sustained winds around 200 miles per hour. Neptune's atmosphere is moving at more than 7 times that speed. On a planet receiving almost no sunlight, roughly 900 times less solar energy per square meter than Earth. Where the energy driving those winds comes from is still not fully understood. Neptune appears to generate significant internal heat, but the exact mechanism and why it produces winds at that scale remains an open question. Voyager 2 also got a close look at Triton, Neptune's largest moon. Triton is unusual for a number of reasons. It orbits Neptune in the opposite direction from the planet's rotation. That strongly suggests it was captured from elsewhere rather than forming in place alongside Neptune. That kind of retrograde orbit is a signature of a captured object. And Triton is geologically active in a way nobody expected. Voyager 2 detected geysers on its surface, erupting nitrogen gas several miles into the thin atmosphere. This is a moon in the outer reaches of the solar system, receiving almost no solar energy. It's venting gas into space. The mechanism appears to involve solar heating of nitrogen ice just beneath the surface, building pressure until it erupts, but doing that on a world that cold, that far from the sun, is genuinely strange. Triton is also slowly spiraling inward toward Neptune due to tidal forces. In roughly 3.6 billion years, it will cross the Roche limit and be torn apart by Neptune's gravity, likely forming a ring system around the planet that would rival Saturn's. What remains unknown about Uranus and Neptune vastly outweighs what we do know. We've never measured their interior pressures or confirmed the composition of their cores with certainty. We don't know precisely how their atmospheres formed or why their chemical makeups differ as they do. The origin of Uranus's peculiar magnetic field remains a genuine puzzle. Neptune's internal heat source continues to elude definitive explanation despite decades of theoretical work. The depths of their lower atmospheres remain completely unexplored territory. These aren't peripheral gaps in our knowledge. They represent fundamental questions about planetary formation and evolution that demand answers. Here's the thing that makes all of this more striking. Voyager 2's flyby of Uranus lasted about 6 hours of close-range observation. Neptune was similar. That's the entire data set from which our direct knowledge of these planets is drawn. Every model, every refined estimate, every scientific paper about their internal structures and atmospheric dynamics is built on a foundation of a few hours of measurements taken by a spacecraft designed in the 1960s and early 1970s. There has been no Cassini for these planets, no Juno. No extended orbital mission collecting years of data. Just a single brief pass by an aging probe that had already spent a decade in space. What makes that even more remarkable is that the data from those flybys has continued to produce results long after the encounters themselves. Scientists have been going back to Voyager 2's archived readings for decades, applying modern analysis techniques to measurements taken with 1970s instruments, finding things that weren't apparent at the time. In 2023 and 2024, scientists sifting through data from that 1986 flyby found what might be evidence of a moon nobody knew existed, which tells you something about how much is still buried in those old transmissions. On February 14, 1990, Voyager 1 turned its camera back toward the inner solar system for the last time. The spacecraft was about 3.7 billion miles from the Sun at that point, already well beyond the orbit of Neptune, already in a part of space no human-made object had occupied before. The images it captured that day were assembled into a mosaic of 60 frames. And somewhere in one of those frames, almost invisible against the darkness, was Earth. Not a world, not a planet with oceans and continents and weather systems. A pale blue dot, a fraction of a pixel. Something you'd miss if you weren't looking for it. Carl Sagan had pushed for this photograph for years. NASA hadn't been enthusiastic. Turning the cameras back toward the sun carried risk. Direct sunlight could damage the imaging instruments. There was also a scientific argument against it. By 1990, Voyager 1 had finished its planetary work. There was no obvious data to collect by photographing the inner solar system from that distance. What Sagan understood, and eventually persuaded enough people to agree with, was that the value wasn't scientific. It was something else entirely. Sagan described the image in a 1994 book. He wrote that every human being who ever lived, every king and farmer and child, every moment of joy and suffering and ambition in all of recorded history had played out on that mote of dust suspended in a sunbeam. Think about what that framing requires you to accept. From 3.7 billion miles away, the entire project of human civilization doesn't register as a shape, it registers as a color. Barely that. The photograph was taken, and then the cameras were shut off. Voyager 1 had no more targets. It wasn't heading toward anything in particular. No planet, no moon, no object anyone had cataloged. It was heading outward. That's all. Outward into a part of the solar system that no instrument had ever directly sampled, toward a boundary that existed in theoretical models but had never been measured by anything that could send data back to Earth. Voyager 2 was on a different trajectory by then, angled downward relative to the plane of the solar system. Both spacecraft were coasting. The planetary flybys that had defined the mission were finished. Jupiter, Saturn, Uranus, Neptune, all of it was behind them now, receding. The spacecraft were running on the momentum of their gravity assists and their original launch velocity with no engine burning, no course corrections being made. Just two metal objects moving through increasingly empty space at roughly 35,000 to 38,000 miles per hour. The Voyager spacecraft had been designed to operate for only 4 years. Yet here they were, more than a decade past that deadline, still transmitting data back to Earth. Their power came from radioisotope thermoelectric generators that converted the heat from decaying plutonium into electrical current. It was an elegant engineering solution to the problem of operating a spacecraft too far from the sun for solar panels to be practical. As long as the plutonium continued to decay and the spacecraft's systems remained operational, they would keep sending signals home through the darkness, reporting on whatever they encountered in the increasingly empty space ahead. That sounds fast. At that speed, you could cross the continental United States in about 5 minutes. But space doesn't care how fast you're moving in human terms. The distances involved make those numbers almost meaningless. It would still take Voyager more than 70,000 years to reach the nearest star system, even at that velocity. The scale of interstellar space makes the fastest thing humans have ever launched look practically stationary. What both spacecraft were heading toward, though the scientists tracking them could only estimate when and where, was the edge of the heliosphere. The sun doesn't just emit light, it constantly exhales a stream of charged particles, the solar wind, that flows outward in all directions at roughly 1,000,000 miles per hour. That wind doesn't go on forever. At some point far beyond the planets, it runs into the interstellar medium. The gas and dust and particles that fill the space between stars pushes back. The solar wind slows. Eventually, it stops. And the boundary where it stops, the heliopause, is where the sun's influence effectively ends. Nobody had ever measured that boundary directly. Scientists had theoretical models for where it should be and what it should look like. They had indirect evidence from observations made with other instruments. But the models disagreed with each other in important ways. Some predicted the heliopause would be relatively smooth and well-defined. Others suggested it might be turbulent, irregular, more complicated than the simple picture implied. Without a spacecraft that could actually travel through it and transmit data from the other side, there was no way to know which models were right. That was where Voyager 1 and Voyager 2 were headed. Slowly, by cosmic standards, relentlessly, by any practical measure. Each year, each spacecraft moved about 3.6 additional astronomical units from the sun, roughly 335 million miles. Year after year, through the 1990s and into the 2000s, the distance grew. The signals grew fainter. The round-trip communication time stretched from hours to most of a day. Engineers at JPL tracked both probes with the Deep Space Network, the large antenna system built specifically to maintain contact with distant spacecraft. The transmissions were still arriving. The instruments were still functioning. The spacecraft were still out there. And somewhere ahead of both spacecraft, still decades away at that point, was a boundary that nobody had ever crossed, the edge of the sun's influence and the cold interstellar space beyond it. The solar system doesn't end at Neptune or at Pluto or even at the scattered disk of icy objects beyond it. The actual boundary, the point where our sun's influence gives way to the broader galaxy, sits much farther out than that. And for most of human history, we had no way to directly measure where it was or what it looked like. We had equations, we had theoretical models, we had estimates. What we didn't have was a spacecraft that had actually crossed through it and reported back. That's the gap the Voyagers were about to close. To understand what they were heading toward, you need to understand what the heliosphere actually is. The sun doesn't just sit there radiating light, it constantly pushes outward a stream of charged particles, mostly electrons and protons, called the solar wind. This isn't a gentle breeze. At Earth's distance from the sun, the solar wind is moving at somewhere between 250 and 500 miles per second. It flows outward in all directions, continuously, carrying with it the sun's magnetic field. That combination, the charged particle stream plus the embedded magnetic field, inflates a vast bubble around the entire solar system. That bubble is the heliosphere. Everything we've ever launched, every planet we've ever visited, every human being who has ever lived has spent their entire existence inside it. Think about what that bubble is actually doing. It's not just background scenery. The heliosphere acts as a shield. Out in the galaxy, there's a constant bombardment of high-energy particles called cosmic rays, fragments accelerated to enormous speeds by supernovae, black holes, and other violent events happening billions of miles away. Left unimpeded, these particles would stream through the inner solar system at significantly higher intensities than they currently do. The heliosphere deflects a substantial fraction of them. It doesn't stop all of them, but it reduces the flux meaningfully. Life on Earth exists inside a magnetic shelter that the sun is continuously generating and maintaining. Most people never think about that. The solar wind doesn't maintain the same properties all the way out, though. As it moves away from the sun, it gradually thins. By the time you're past Neptune, the particle density is orders of magnitude lower than it is near Earth. But the wind is still moving, still supersonic, still pushing outward. At some point, the solar wind has to run into something. That something is the interstellar medium, the gas, dust, and particles that fill the space between stars. The interstellar medium isn't vacuum. It has its own pressure. And as the solar wind gets farther from the sun and loses energy, there's a point where that outward push and the inward pressure of interstellar space reach a confrontation. The first major boundary you'd hit if you traveled outward from the sun is called the termination shock. This is where the solar wind abruptly slows from supersonic to subsonic speed. Before the termination shock, the solar wind is moving faster than the speed of sound in that medium, fast enough that information about what's ahead of it can't propagate backward through the wind itself. Then it hits the pressure from the interstellar medium and it slows sharply. The transition isn't gradual. It's a shock, an abrupt deceleration, similar in principle to the sonic boom a supersonic aircraft creates when it crosses the sound barrier. But in reverse, The solar wind goes from traveling at several hundred miles per second to something considerably slower, all within a relatively thin boundary layer. Beyond the termination shock, the solar wind doesn't stop. It continues outward, but now it's moving slowly and it's turbulent. This region, between the termination shock and the outer boundary of the heliosphere, is called the helios sheath. The helios sheath is where the slowed, compressed solar wind piles up before it eventually merges with the interstellar medium. Scientists expected this region to be turbulent and magnetically complex, but the degree to which it would actually complicate their models wasn't something they'd be able to assess until something crossed through it. The outermost boundary is the heliopause. This is the true edge of the heliosphere, the surface where the solar wind pressure and the interstellar medium pressure finally equalize. Inside the heliopause, you're in the sun's domain. Outside it, you're in interstellar space. The heliopause isn't a hard wall, it's a dynamic surface that moves in and out depending on the activity of the sun and the local conditions of the interstellar medium. During periods of high solar activity, when the sun is pushing harder, the heliopause gets pushed outward slightly. During quiet periods, it contracts. It's a boundary that breathes. Scientists have been modeling all of this for decades before Voyager came along. The basic theoretical framework came together in the 1950s and 1960s, built primarily on plasma physics and magnetohydrodynamics, the study of how magnetic fields and conducting fluids interact. The models predicted where the termination shock should be, roughly. They predicted the existence of the helios sheath. They predicted the heliopause. Some estimates put the termination shock at around 75 to 90 astronomical units from the Sun, where 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. That would place the heliopause somewhere beyond 100 astronomical units. But all of that was inference. It was built on physical principles and mathematical extrapolation, not measurement. Nobody had ever put an instrument through the termination shock. Nobody had ever sampled the helios sheath directly. Nobody had detected the heliopause from the inside and watched the solar wind particle counts drop. The models were plausible, internally consistent, and built on sound physics. They were also completely untested against reality. Voyager 1 launched in 1977. It passed Neptune's orbit. It passed Pluto's orbit. It crossed the outer edges of the scattered disk. And it kept going, still transmitting, instruments still running, heading toward a boundary that existed, as far as anyone could prove, only on paper. The problem was that everything scientists knew about the heliosphere's edge was theoretical. Nobody had ever sent anything through it, and Voyager 1 was about to change that. The termination shock is where the solar wind hits a wall, not a physical wall, but a boundary where it abruptly runs out of momentum and slows from supersonic to something much slower. Think about what that actually means. The solar wind has been streaming outward from the sun at roughly 400 miles per second. It crosses the orbits of Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune without slowing down significantly. Then, somewhere beyond Neptune, it runs into the pressure of interstellar space pushing back, and it stops being supersonic. That transition, that shock, is the termination shock. Scientists had theoretical reasons to expect it. The models predicted it. What they didn't know was exactly where it would be, what it would look like up close, or whether the boundary would be clean and well-defined or something messier. Voyager 1 crossed the termination shock in December 2004 at roughly 94 astronomical units from the Sun. That's 94 times the distance from the Earth to the Sun, or about 8.7 billion miles out. Voyager 2 followed in August 2007, crossing at around 84 astronomical units. The fact that Voyager 2 crossed closer to the Sun than Voyager 1 was itself a surprise. It meant the heliosphere isn't a perfect sphere. The boundary shifts. It breathes with the solar cycle, expanding when solar activity is high and contracting when it's low. When Voyager 1 crossed the termination shock, its instruments recorded exactly what the theory predicted in broad strokes. The solar wind slowed abruptly, the magnetic field compressed and intensified, and the density of charged particles changed. But the details were strange. The crossing wasn't a single clean event. Voyager 1 appears to have crossed back and forth across the boundary multiple times as the shock itself moved. The termination shock is dynamic. It doesn't hold still. It moves inward and outward in response to variations in solar wind pressure, which meant the spacecraft encountered a fluctuating boundary rather than a fixed line. Voyager 2's crossing was more informative in one important respect. It still had a working plasma science instrument. Voyager 1's equivalent instrument had failed back in 1980, which meant direct plasma measurements weren't available for that crossing. When Voyager 2 hit the termination shock, its plasma instrument caught the solar wind speed, dropping from around 300 miles per second to roughly 100 miles per second in a very short distance. You're looking at the solar wind losing about 2/3 of its velocity almost instantly. The magnetic field jumped. The temperature of the plasma spiked. And then both spacecraft were through, into the heliosheath. Here's where things got genuinely uncomfortable for the theorists. The heliosheath was supposed to be a relatively well-understood region. The models described it as a zone of turbulent, slowing solar wind filling the space between the termination shock and the heliopause, the outermost boundary of the Sun's influence. Turbulent, yes. Unexpected, not really. That was the assumption. The reality was different. The solar wind in the heliosheath behaved strangely. Scientists expected it to continue flowing outward even after slowing at the termination shock, gradually losing speed until it reached the heliopause. Instead, Voyager 2's plasma data showed the outward component of the solar wind essentially dropping to zero well before the heliopause. The wind wasn't flowing out anymore. It had been deflected sideways, pushed around the edge of the heliosphere by the pressure of the interstellar medium outside. This was not what the standard models had described. The magnetic field in the heliosheath was also more complicated than anticipated. The solar magnetic field gets dragged outward by the solar wind, spiraling as the Sun rotates, what's called a Parker spiral. Past the termination shock, that spiral gets compressed and tangled. Voyager 1 spent years crossing through this region, and its magnetometer was recording field configurations that didn't match the models well. The field was strong in places it wasn't supposed to be. It fluctuated in ways that suggested the heliosheath is a region of genuine magnetic complexity, not the relatively smooth environment the textbooks implied. There was also the question of energetic particles. In the heliosheath, both spacecraft measured increased levels of particles bouncing back and forth along magnetic field lines, particles that had been accelerated at the termination shock and were now trapped, in a sense, in the space beyond it. Voyager 1 detected a steady rise in high-energy galactic cosmic rays beginning to filter in from outside. At the same time, lower-energy solar particles were still present. The heliosheath is a mixing zone, a transitional environment where solar influence and interstellar influence are both present in ways that defy a clean separation. Voyager 1 spent roughly 8 years crossing the heliosheath before reaching the heliopause. 8 years of instruments collecting data in a region no probe had ever entered before. Voyager 2 took about 11 years. That's a vast amount of data from an environment that scientists had only been able to model theoretically until those spacecraft arrived. And consistently, the measurements complicated the clean picture the models had offered. The boundary regions were thicker than expected. The plasma behavior was stranger. The magnetic field was more tangled. And sitting just ahead of both spacecraft, still years away at the time of the termination shock crossing, was the heliopause itself, the true edge of the sun's reach, waiting to see whether it would behave any better than everything that came before it. Everything between the termination shock and the outer edge of the heliosphere, a region called the Helios Heath, turned out to be more turbulent, more magnetically complex, and more surprising than the models had suggested. On August 25, 2012, a spacecraft launched in 1977 crossed into interstellar space, and it took scientists almost a year to be completely certain that's what had happened. That uncertainty wasn't a failure. It was a reflection of just how hard it is to confirm something that has never been done before, with instruments that were designed for an entirely different mission, measuring an environment that no model had perfectly predicted. Voyager 1 was 122 astronomical units from the Sun when it happened. That's 122 times the distance from Earth to the Sun, roughly 11 billion miles. A signal from the spacecraft took about 17 hours to reach Earth. And the boundary it crossed, the heliopause, had never been physically sampled by anything humans had ever built. Here's what the instruments actually recorded. Starting in May 2012, Voyager 1 began detecting a steady rise in high-energy particles, cosmic rays, the kind produced by supernova explosions billions of miles away across the galaxy. At the same time, the low-energy particles associated with the solar wind started dropping. This was expected in broad terms. Scientists knew that crossing the heliopause should mean moving from a solar-dominated environment to a galactic one. But the change, when it came, was far more dramatic than the models had suggested it would be. On August 25th, the number of charged particles originating from the Sun dropped by a factor of roughly 1,000. In the same window, galactic cosmic ray counts jumped by about 9%. Both changes happened fast. Not grady, fast. Think about what that means. One day you're in an environment flooded with particles streaming outward from our Sun. The next day, those particles are essentially gone, and what's hitting your detectors instead is radiation from the wider galaxy. That's not a gradual transition. That's a boundary. But here's where things get complicated. To truly confirm that Voyager 1 had crossed the heliopause, scientists needed plasma data, direct measurements of the charged gas surrounding the spacecraft. And Voyager 1's plasma science instrument had stopped working in 1980. 32 years before the crossing it was supposed to help detect, that instrument went silent. So the team couldn't just look at the plasma readings and say, yes, the density jumped, we're through. They had to find another way. What they used instead was the plasma wave subsystem, an instrument designed to detect oscillations in plasma, essentially vibrations moving through the charged particles around the spacecraft. Plasma oscillations occur at a frequency that depends directly on electron density. More electrons packed into a given volume means higher frequency oscillations. Lower density means lower frequency. If scientists could detect those oscillations and measure their frequency, they could calculate the electron density of whatever environment Voyager 1 was moving through, even without a functioning plasma science instrument. The opportunity came from an unlikely source. In March 2012, the Sun released a large burst of energy, a solar outburst that sent a pressure wave propagating outward through the heliosphere. That wave eventually reached Voyager 1. When it did, It caused the plasma around the spacecraft to ring, producing plasma oscillations that the wave subsystem could measure. The oscillations were detected beginning on April 9, 2013, more than 7 months after the August crossing. When the team analyzed the frequency of those oscillations, the number they got back was stark. Electron density in the region surrounding Voyager 1 was about 80 times higher than it had been inside the heliosphere. Not 10 times higher, not 20, 80 times. That was the eureka moment. The very definition of the heliopause is built around exactly that kind of density jump, the point where you transition from the thin, hot plasma of the solar wind to the colder, denser plasma of the interstellar medium. An 80-fold increase in electron density wasn't ambiguous. It wasn't a measurement that could be explained away by instrument noise or modeling assumptions. It was direct evidence that Voyager 1 was somewhere new, somewhere no human-made object had ever been before. Scientists officially confirmed the crossing in a paper published in Science in September 2013. The date they assigned to it, August 25, 2012, was based on when the particle population shifted so sharply. But the confirmation itself required nearly a year of analysis, a fortuitous solar event, and a creative use of an instrument that was never intended to be the primary tool for detecting the heliopause. That's not a footnote. That's actually part of what makes this story worth paying attention to. You don't always get clean data. Sometimes you have to work with what you have. Now step back and consider what you're actually looking at when you think about August 25, 2012. Voyager 1 launched on September 5, 1977. It was built to survive a 5-year planetary tour. The scientists and engineers who designed it were working with computing power that would embarrass a modern calculator. The transmitter on board produces 22 watts of power, about the same as a refrigerator light bulb. By the time the heliopause crossing happened, the signal arriving at Earth from Voyager 1 was so faint that the receiving antennas of NASA's Deep Space Network had to be pointed with extraordinary precision just to detect it at all. And yet that 22-watt signal, crossing 11 billion miles of space, delivered the data that confirmed humanity's first entry into interstellar space. The particles flooding in from across the galaxy weren't a poetic detail. They were real measurements, galactic cosmic rays produced by stellar explosions that happened before the sun existed, now hitting the detectors of a spacecraft built in California in the 1970s. The plasma density that confirmed the crossing was calculated from oscillations moving through charged particles that no human had ever directly touched. Every number that came back from Voyager 1 in those weeks was a measurement of something that had never been measured before, by anything, ever. There's a version of this story that focuses on the engineering triumph, the spacecraft that outlasted its design life by 4 decades and crossed the boundary of the solar system on a refrigerator bulb worth of power. That version is true, and it's remarkable, but the scientific dimension is equally significant. The heliosphere's edge wasn't just a milestone on a map. It was a physical boundary between 2 distinct environments, and Voyager 1 crossed it and sent back the data to prove it. The particle drop, the cosmic ray spike, the plasma oscillations, the 80-fold density jump. Each measurement added to a picture that nobody had ever been able to draw from direct observation before. It was, by any measure, the moment a human-made object left the solar system for the first time, and the data it sent back in those weeks remains some of the most scientifically significant ever transmitted. Once Voyager 1 was through the heliopause, the instrument started returning data from an environment nobody had ever directly sampled. That distinction matters. Everything scientists knew about interstellar space before 2012 came from observations made at a distance, telescope readings, theoretical models, inferences drawn from how light and particles behaved across billions of miles. Voyager 1 was the first object from Earth to actually sit inside the very local interstellar medium and take readings. And what it found was not what the models had fully prepared anyone for. The first thing the instruments confirmed was that the plasma out there is significantly denser than the plasma inside the heliosphere. This part wasn't a total surprise. Scientists had expected some increase in density beyond the heliopause. Since the interstellar medium is a different physical environment from the sun's own bubble, but the degree of it was striking. Inside the heliosphere, the plasma is tenuous and hot, spread thin by the expanding solar wind. Outside, it's cold and compressed. The boundary between those two environments is sharp enough that crossing it registers immediately in the data. Voyager's instruments showed the shift clearly. Then there's the temperature reading, which is where things get strange. At the heliopause itself, the measured temperature runs somewhere between 30,000 and 50,000 Kelvin. To put that in perspective, the surface of the sun is about 5,800 Kelvin. So on paper, Voyager 1 passed through something far hotter than the surface of our own star. That sounds like it should be catastrophic. It wasn't. The reason is particle density. Temperature in a plasma is a measure of how fast individual particles are moving, not how much heat energy is present in a given volume. At the heliopause, the particles are moving at extreme speeds, but there are so few of them that almost no heat transfers to anything they encounter. The spacecraft passed through what looks numerically like an inferno and barely felt it. It's one of those results that sounds wrong until you think carefully about what temperature actually means in near-vacuum conditions. Beyond the heliopause, Voyager continued moving outward through the very local interstellar medium. Scientists call this region the VLISM. Voyager 1 has now been traveling through it for more than a decade. What the probe has been finding is that this region isn't featureless, it has structure. The electron density doesn't stay constant as Voyager moves deeper. It increases. Measurements compiled over the years since the crossing show a clear and persistent density gradient. The interstellar medium is getting slightly denser in the direction Voyager is heading. Scientists reported this finding formally in 2020. It implied something significant. The very local interstellar medium has large-scale features that weren't fully captured in earlier models. The space between stars isn't just a uniform fog. It varies. It has texture, in a sense. And the only reason we know that is because Voyager 1 has been moving through it long enough and far enough to actually measure the change. This connects to another discovery that predates the Voyager crossing but gets a lot clearer once you understand what Voyager found afterward. In 1992, the two Voyager spacecraft detected evidence of a hydrogen wall at the outer edges of the solar system. NASA confirmed this formally in 2018, drawing on data from the New Horizons spacecraft as well. The hydrogen wall is essentially a concentration of neutral hydrogen atoms that piles up at the boundary between the outward-pushing solar wind and the interstellar medium. As the solar wind slows and loses momentum approaching the heliopause, it stops carrying hydrogen outward as efficiently. That hydrogen accumulates. The result is a detectable wall of neutral hydrogen sitting at the edge of the heliosphere. It's not a physical barrier in the way a wall usually implies. You couldn't crash into it, but it's a real structure, measurable from a distance by the way it scatters ultraviolet light. Voyager's crossing confirmed that it's there. Think about what that means. The solar system is enclosed in its own bubble. That bubble has a visible edge, not just a theoretical one. One of the more unexpected results from Voyager One's time in the VLISM came not from a dramatic boundary crossing, but from a slow accumulation of data over years. Researchers monitoring the spacecraft's plasma wave subsystem noticed that the instrument was picking up oscillations. The plasma surrounding Voyager wasn't completely still, it was vibrating. Faint, persistent, consistent waves moving through the electron population in the interstellar medium. These oscillations allowed scientists to measure the local electron density indirectly by essentially listening to how the plasma resonated at different frequencies. The denser the plasma, the higher the frequency. The method had been used before to infer conditions during specific events. But what was different here was the continuity. The signal didn't just appear in response to a solar outburst or a sharp boundary crossing. It kept going. Quiet, steady, ongoing vibration in the plasma of interstellar space. By 2021, the electron density measurements from those oscillations had become one of the most reliable ongoing data sets Voyager 1 was producing. And they showed something consistent with the broader density gradient finding, beyond 160 astronomical units from the Sun. The electron density was stabilizing at around 0.147 electrons per cubic centimeter. That is roughly 80 times denser than what Voyager measured inside the heliosphere. Some researchers suggested this might indicate Voyager had entered a new regime of the interstellar medium, a distinct zone with its own characteristics, separate from the chaotic transition region just beyond the heliopause. The picture of interstellar space that's emerging from Voyager 1's data isn't a uniform void, it's layered. It has gradients and regions and features spread across astronomical distances. What makes all of this especially striking is the instrument doing the measuring. Voyager 1's plasma science instrument stopped working in 1980. The probe has been in interstellar space without a direct plasma detector for the entire time it's been out there. Everything scientists have learned about the plasma environment in the VLISM from Voyager 1 has come from indirect methods, using plasma waves, inferring density from oscillation frequencies, reading particle behavior through instruments designed for entirely different purposes. The fact that any of this is possible speaks to how creatively the team at JPL has been able to work with a spacecraft that was never designed to do what it's doing now. And in 2020, the plasma wave instrument detected something that scientists described as a persistent hum, the vibration of interstellar plasma, carrying on endlessly in the space between stars. 6 years after Voyager 1's crossing, its twin exited the heliosphere on November 5, 2018. And because Voyager 2 still had a working plasma science instrument that Voyager 1 had lost in 1980, scientists got to watch the transition in a way that had been impossible the first time. That distinction matters more than it might sound. When Voyager 1 crossed the heliopause in 2012, the confirmation process was complicated. The plasma science instrument had gone silent in 1980, which meant scientists couldn't directly measure the solar wind. They had to piece together the crossing from particle counts, magnetic field readings. Eventually, the plasma wave oscillations that gave them that 80-fold density jump. It worked, but it was indirect. It was inference. With Voyager 2, they had the real thing, a functioning instrument that could measure the plasma surrounding the spacecraft in real time. What it recorded on November 5, 2018 was unambiguous. The solar wind simply dropped to zero. Think about what that means. For over 41 years, Voyager 2 had been moving through a medium defined by the Sun, a constant outward flow of charged particles streaming away from our star at hundreds of kilometers per second. That flow had been present every single day since launch, gradually weakening as the spacecraft moved farther out, but always there. And then, on a specific day, it stopped. The plasma science experiment registered the reading, and the solar wind was gone. Voyager 2 was in interstellar space. The crossing itself happened faster than expected. Both the heliopause and the transition zone around it were sharper and narrower than the models had predicted. Voyager 2 moved through the boundary region in a matter of days rather than weeks. The heliosheath, the turbulent region between the termination shock and the heliopause, had been messy and unpredictable, with the boundary wobbling in response to solar activity. But the heliopause itself turned out to be relatively thin. You were inside the heliosphere, and then fairly quickly you weren't. What Voyager 2's plasma instrument also revealed was something about the temperature on either side of that boundary. Inside the heliosphere, near the heliopause, the plasma is hot, extremely hot, in the tens of thousands of Kelvin range. Outside, in the interstellar medium, the plasma is cooler. But Voyager 2 detected that the plasma just outside the heliopause was slightly warmer than the models had expected, and slightly more compressed. That compression suggested something was squeezing the plasma around the outer edge of the bubble. The heliosphere, as it moves through the interstellar medium, appears to push the surrounding material up against itself, a kind of bow pressure that elevates the density and temperature right at the interface. The density numbers confirmed something that Voyager 1 had also hinted at. The interstellar medium is significantly denser than the plasma inside the heliosphere. That's not surprising in principle. The heliosphere is essentially an inflated bubble pushing outward against the surrounding galactic environment. So the material inside it is more diffuse. But the specific numbers, measured directly for the first time by two functioning spacecraft, gave scientists real data to work with instead of estimates. Here's where things got genuinely complicated. As Voyager 2's data came in and scientists compared it carefully to what Voyager 1 had found, a picture emerged that didn't fit the clean theoretical model of a sealed, self-contained bubble. The heliosphere leaks, and it leaks in both directions. Voyager 1 had detected interstellar particles threading into the heliosphere, tendrils of material from outside pushing inward through the boundary, like roots through cracked stone. That was surprising enough, but Voyager 2 found the reverse: low-energy particles of solar origin extending more than 100 million miles beyond the heliopause, out into interstellar space on the other side. Solar material was bleeding outward past the boundary. The two findings together painted a picture of a boundary that is not a wall. It's more like a membrane, and it's a permeable one. This is a significant revision of how scientists had thought about the heliosphere. The simple model, solar wind pushes outward, hits the interstellar medium, forms a clean outer edge, turns out to be an oversimplification. In reality, the boundary is dynamic. Material crosses it in both directions. The solar magnetic field drapes around the heliopause rather than stopping cleanly at it. The interstellar magnetic field on the outside is oriented differently than expected, a more complicated interface than any of the pre-Voyager models had described. Why does this matter? Because the heliosphere has a job. It shields everything inside it, including Earth, including you, from a significant portion of the galactic cosmic radiation that permeates the space between stars. If the boundary is leaky, that means the shielding isn't perfect. It was never claimed to be, but the degree of permeability matters for understanding just how much protection the inner solar system actually gets. Voyager 2's measurements gave scientists better numbers to work with on that question. What also came out of the Voyager 2 data was a more detailed picture of the boundary's geometry. Voyager 1 crossed the heliopause at about 122 astronomical units from the Sun. Voyager 2 crossed at roughly 119 astronomical units, slightly closer in. on a different trajectory heading in a different direction through the sky. The fact that the two crossings happened at different distances in different directions is itself a data point about the shape of the heliosphere. That is not perfectly symmetrical. The side of the heliosphere facing into the direction of the sun's motion through the galaxy is compressed, pushed in by the interstellar medium. The side trailing behind is thought to extend much farther. Two crossings at slightly different distances heading in slightly different directions is beginning to give scientists a sense of how asymmetrical that shape actually is. Voyager 2 also confirmed that the region just beyond the heliopause is not clean interstellar space. Both spacecraft appear to be in what's called the very local interstellar medium, a transitional zone that's still being influenced by the heliosphere's presence nearby, rather than the undisturbed galactic environment farther out. True interstellar space, in the sense of a region completely unaffected by our sun, is still ahead of both probes. The heliosphere wasn't the sealed protective bubble the models had described. It was leaky in both directions, with interstellar material threading inward and solar material bleeding out, a dynamic and permeable boundary that forced a significant revision of the theoretical picture. One of the things the Voyager crossings confirmed in the most direct possible way is that the heliosphere is doing something genuinely important for everything living inside it. That might sound obvious. You've probably heard that space is dangerous, that radiation is a problem, that astronauts on long missions face elevated cancer risk. But knowing something in the abstract and having a spacecraft measure it directly at the actual boundary are two very different things. What Voyager found at the heliopause gave scientists their first direct look at just how much the sun's bubble is actually doing for us. Here's what cosmic rays are. They're not rays in any conventional sense. They're high-energy particles, protons, electrons, atomic nuclei, accelerated to enormous speeds by some of the most violent events in the galaxy. Supernova explosions, colliding neutron stars, black holes consuming matter. These events fling particles outward to velocities approaching a substantial fraction of light speed, and these particles travel more or less indefinitely until they hit something. The galaxy is full of them. They're moving through interstellar space in every direction constantly, at energies that can penetrate metal and damage living tissue at the cellular level. Some of the most energetic cosmic rays carry more kinetic energy than a well-thrown baseball packed into a single subatomic particle. Think about that for a second. Done. Inside the heliosphere, the solar wind and the sun's magnetic field create a kind of interference. The outward pressure of the solar wind pushes back against incoming cosmic rays, deflecting lower energy particles and reducing the overall flux that reaches the inner solar system. It's not perfect. Some cosmic rays get through regardless. But the heliosphere significantly reduces the dosage that anything inside it receives. Earth's atmosphere handles what gets past, but planets without thick atmospheres, or spacecraft or astronauts, are more directly exposed. The heliosphere is, in a practical sense, a radiation shield that covers the entire solar system. When Voyager 1 crossed the heliopause in 2012, the cosmic ray instrument showed exactly what scientists had theorized but never directly confirmed. The count jumped, not gradually, not over weeks, sharply in the data as the spacecraft moved from the heliosheath into interstellar space. On August 25, 2012, the probe recorded roughly a 9% increase in fast-moving galactic cosmic rays in the space of a single day. That number sounds modest, but it represented the unfiltered interstellar environment, particles that the heliosphere had been blocking, now arriving without interference. The solar origin low-energy particles dropped away at the same time, replaced by the background radiation of the galaxy itself. Voyager 2 confirmed the same pattern 6 years later. Both crossings showed the same basic transition, solar particles dropping sharply, galactic cosmic rays rising. 2 data points, same result. The heliosphere's shielding effect isn't subtle or theoretical anymore. It's measured. The instruments recorded it happening in real time. Now here's where things get genuinely strange. At the heliopause itself, the temperature readings were extraordinary. The boundary between the solar wind and the interstellar medium registered between 30,000 and 50,000 Kelvin. Some descriptions of this region have used the phrase wall of fire, which is technically accurate and also deeply misleading. 50,000 Kelvin is hotter than the surface of most stars. If you imagined flying a spacecraft through a region of space at that temperature, you'd expect it to be instantly destroyed. It wasn't. The spacecraft sailed through without any thermal damage at all. The reason for that is particle density. Temperature in plasma physics describes how fast individual particles are moving, but if there are almost no particles present, it doesn't matter how fast they're moving. There simply aren't enough of them to transfer meaningful heat to any object passing through. The heliopause is extraordinarily hot in the sense that individual particles carry enormous energy. It's also extraordinarily empty. The chances of any given particle actually colliding with the spacecraft were so low that the effective heat transfer was negligible. The Voyager probes passed through what sounds like an inferno and felt essentially nothing. That paradox is worth sitting with. A region of space that would register as millions of degrees under some measurement frameworks, and that is simultaneously harmless to pass through, because there's almost nothing there. The interstellar medium doesn't behave the way intuition suggests, but cosmic rays are a different story. Unlike the sparse plasma at the heliopause, cosmic rays aren't just heat, they're particles with enough energy to punch through shielding. High-energy cosmic rays don't stop at the outer hull of a spacecraft. They deposit radiation dose. They damage DNA. They produce secondary particles when they interact with matter, which can actually make the situation worse rather than better. The shielding strategies that work against solar radiation in the inner solar system are only partially effective against the higher-energy galactic variety. Beyond the heliopause, the environment that Voyager 1 has been traveling through isn't empty. It's filled with this background radiation. Every year that Voyager spends in the interstellar medium, its instruments register the ongoing cosmic ray environment that exists throughout the galaxy. That environment is not welcoming. It's not catastrophically lethal in the way a solar flare might be close to the sun, but it is persistent, penetrating, and cumulative. A human crew spending years beyond the heliopause would be absorbing a radiation dose that current shielding technology cannot fully mitigate. The numbers from Voyager don't offer any easy solutions. They simply describe what's out there. The intensity is higher than inside the heliosphere. The particle energies are higher. The sources are distributed across the entire galaxy and can't be predicted or avoided the way solar events can. Any serious engineering proposal for crewed interstellar travel has to account for this, and accounting for it means mass, thick shielding, which means heavy spacecraft, which means the propulsion problem gets harder. For anyone thinking seriously about sending humans beyond the heliopause someday, Voyager's cosmic ray data is among the most sobering numbers the mission has produced. Before Voyager reached the heliopause, scientists had models for how the magnetic fields at the boundary should behave. The models weren't wild guesses. They were built from decades of theoretical work, solar wind observations, and indirect measurements. But like most of what Voyager encountered out there, the reality turned out to be considerably more complicated than what the models had described. The basic picture scientists expected was this: the sun constantly pushes a stream of charged particles outward in every direction. That solar wind carries the sun's magnetic field with it, stretching it out across the entire heliosphere. As the solar wind approaches the heliopause and runs out of momentum, those magnetic field lines were expected to pile up and drape around the boundary, the way water builds up in front of a slow-moving dam. That part turned out to be roughly correct. Voyager did measure a magnetic field that intensified as it approached the heliopause. In fact, the field in that region was about 10 times stronger than what Voyager had measured before crossing the termination shock, which was already significantly elevated from its baseline readings farther inside the heliosphere. The compression was real. The draping was real. That much the models got right. What they didn't get right was the interstellar magnetic field on the other side. Before Voyager crossed over, the best estimates placed the interstellar magnetic field outside the heliosphere at a particular orientation, one that scientists had inferred from indirect observations and theoretical reasoning about the way nearby interstellar matter is distributed. When Voyager 1 crossed the heliopause in 2012 and started measuring the field directly, the orientation it found was different from what had been predicted. Not dramatically different, but measurably, clearly different. The interstellar field wasn't lined up the way the models said it should be. That misalignment meant the two fields, the draped solar field on one side and the interstellar field on the other, met at the heliopause at an angle nobody had fully anticipated. The interface wasn't a simple handoff between two compatible environments. It was a more tangled, discontinuous transition with field lines changing direction sharply at the boundary. Scientists call this kind of structure a tangential discontinuity. The plasma doesn't cross, but the field orientation shifts abruptly. Think about that for a second. The edge of our solar system isn't just a change in particle density. It's also a place where the magnetic geometry of two completely different environments collides. Voyager 2's crossing in 2018 added more detail. Its instruments confirmed the draping structure, and they showed that the solar magnetic field lines wrap tightly around the outside of the heliopause, rather than threading through it. The boundary holds the two field environments largely separate, even as particles leak across it in both directions. But the geometry of that wrapping and the precise orientation of the interstellar field just outside continue to create headaches for the theoretical models. The heliopause wasn't a smooth, symmetrical surface. It was irregular. The field behavior reflected that. Then came 2020. Voyager 1 was at about 149.3 astronomical units from the Sun, roughly 13.9 billion miles out. The spacecraft had been in interstellar space for 8 years at that point, and the magnetometer recorded a sudden, distinct jump in field strength. Not a gradual rise, a step change. The field increased and then persisted at that elevated level, forming what researchers have described as a hump, a region of anomalously strong magnetic field that Voyager has continued measuring as it moves deeper into the interstellar medium. This wasn't predicted. Nothing in the standard models of the very local interstellar medium had prepared scientists for a persistent elevated field structure at that distance and in that direction. Several explanations have been proposed. One possibility is that the hump reflects a large-scale compression wave moving through the interstellar medium, perhaps driven by some energetic event, a supernova or stellar wind interaction somewhere in the galactic neighborhood, that sent a pressure front rippling through the local interstellar gas and field. Another possibility is that the structure relates to how the interstellar medium is organized in the specific direction Voyager 1 is traveling. which happens to be roughly toward the nose of the heliosphere, the leading edge of the sun's motion through the galaxy. The heliosphere isn't stationary. The sun is moving through the interstellar medium at about 43,000 miles per hour, and on the side facing that direction of travel, material piles up. Voyager 1 crossed the heliopause near that nose region. What it's measuring now may reflect large-scale structure in the interstellar medium that's been shaped by the heliosphere's motion over millions of years. But that's still speculative. The hump is real. The measurements are solid. The explanation isn't. What Voyager's magnetic field data has made clear, more than anything else, is that the environment surrounding our solar system isn't uniform or featureless. The very local interstellar medium has structure. It has large-scale gradients, anomalous regions, and field configurations that don't match the simplified background models scientists were working with before any spacecraft had been there to check. The heliosphere sits inside this environment, shaped by it, and in turn, shaping it. The interaction at the boundary is dynamic and complex in ways that are still being worked out. Voyager 1 is now past 160 astronomical units and still measuring. The magnetic field data it returns, faint signal after faint signal crossing more than 22 hours of space to reach the antennas on Earth, continues to complicate the picture in productive ways. Every reading is from a place no instrument has been before. The persistent magnetic hump that Voyager 1 has been measuring since 2020 still doesn't have a complete theoretical explanation, which is the kind of thing that tends to keep astrophysicists up at night. Both Voyager spacecraft are powered by the same basic technology they launched with in 1977, radioisotope thermoelectric generators that convert heat from decaying plutonium into electricity. There's no solar panel on either spacecraft. At the distances they're operating, sunlight is far too weak to be useful. Instead, each probe carries a plutonium core that generates heat as the radioactive material decays, and that heat gets converted into electrical power through a device called a thermoelectric converter. It's not efficient in the way a modern battery or solar array would be, but it doesn't need to be. It just needs to keep working year after year, decade after decade, with no maintenance and no repair. The problem is that plutonium decays. That's the whole point. And as it decays, it produces less heat. Each Voyager loses roughly 4 watts of electrical power every year. 4 watts doesn't sound like much, but over 47 years, those losses add up to something close to 200 watts, power that no longer exists and can't be recovered. When the spacecraft launched, each RTG produced around 470 watts. Today, they're generating somewhere around 250. Think about that for a second. You're trying to run a spacecraft from beyond the solar system on the power equivalent of a few LED light bulbs. That power decline has forced some genuinely painful choices. Every few years, the engineering team at JPL has to sit down and decide which instruments to turn off. You can't keep everything running, the budget won't allow it. So they weigh the scientific value of each instrument against the power it consumes, and then they start switching things off. Heaters go first when possible, then instruments that are considered less critical to the mission's core scientific goals. Some of those decisions are straightforward, others are not. Turning off a heater on a fuel line, for instance, risks freezing the propellant and losing attitude control entirely. Engineers have had to model every scenario carefully before cutting anything. The communication challenge compounds all of this. Voyager 1 is currently more than 15 billion miles from Earth. A radio signal traveling at the speed of light takes over 22 hours to reach the spacecraft one way. That means if you send a command today, you won't know if it worked until tomorrow. If something goes wrong in the meantime, There's no way to intervene in real time. You send the command, and then you wait. And the signal itself is extraordinarily faint by the time it arrives. The Deep Space Network, the array of large radio antennas NASA uses to communicate with distant spacecraft, has to listen very carefully to pick it out of the background noise of space. In 2023, the team discovered that one of Voyager 1's flight data system computers was producing garbled readouts. The data coming back made no sense. For several months, the spacecraft was essentially unable to transmit usable science or engineering data. The team spent weeks analyzing the problem with a 22-hour communication delay on every exchange, trying to diagnose a hardware fault in a 46-year-old computer they couldn't touch. They eventually traced the issue to a corrupted memory chip, a single faulty chip in the flight data system, and found a way to work around it by redistributing the affected code across other memory locations. It worked. Voyager 1 came back online. That fix, executed remotely across more than 15 billion miles, is one of the more remarkable feats of engineering in the mission's history. Voyager 2 has had its own complications. In 2020, the spacecraft unexpectedly switched into fault protection mode and turned off its science instruments. The team managed to bring it back, but the episode underscored how fragile the situation has become. These spacecraft weren't built to last 47 years. The fact that they're still operating at all reflects both the quality of the original engineering and the ingenuity of the people who've kept them alive. But ingenuity only goes so far when the hardware is 5 decades old and the power supply keeps shrinking. The instrument shutdown decisions have accelerated in recent years precisely because the power margins are so thin. When engineers determine that an instrument is drawing more power than the mission can sustain, it gets turned off permanently. There's no turning it back on later. Once the power budget is allocated and the instrument is shut down, that chapter of the mission is closed. Each shutdown reduces what the spacecraft can tell us, but it also buys time for the instruments that remain. The trade-off is always the same. Lose some science now to preserve the possibility of more science later. That's exactly what happened in April 2025 with the low-energy charged particles experiment on Voyager 1. The LECP had been running almost continuously since launch, nearly 48 years of operation. It was designed to measure the energy and composition of charged particles, and in interstellar space, that kind of data has real scientific value. But the power budget had reached a point where something had to go. The team identified the LECP as the most effective instrument to shut down in terms of power savings relative to its current scientific contribution, given where Voyager 1 is and what it's measuring. So they sent the command, waited 22 hours, and the instrument went offline. What's left on each spacecraft is a small collection of instruments that continue to return data about the interstellar medium, magnetic fields, plasma waves, cosmic ray fluxes. That data is still coming in. Scientists are still analyzing it. The mission is still producing science. But the window is closing, and everyone working on it knows that. At some point in the next several years, the power will drop below the threshold needed to operate any science instrument at all, and the transmission will go quiet. Until then, the team at JPL keeps sending commands, keeps listening for the reply, and keeps finding ways to squeeze a little more life out of two machines that should have stopped working decades ago. As of 2025, NASA had shut down the low-energy charged particles instrument on Voyager 1 to conserve power, a decision that tells you everything about where things stand with a spacecraft that is running out of time but hasn't stopped working yet. One of the things two Voyager probes crossing into interstellar space cannot definitively answer is what our heliosphere actually looks like from the outside. Think about what you actually have. Two spacecraft, two crossing points, one on the side of the heliosphere facing roughly toward the constellation Ophiuchus, the other on the opposite flank. Voyager 1 crossed the heliopause at about 100 to 22 astronomical units from the Sun. Voyager 2 crossed at roughly 119 astronomical units, but in a different direction entirely, and 6 years later. Those two numbers sound similar. They're not the same thing. Two measurements taken at different times, in different directions, through a boundary that we now know isn't even stable. That's what scientists are working with when they try to reconstruct the overall shape of the structure that surrounds our entire solar system. Before the Voyagers reached the edge, the dominant models assumed the heliosphere was roughly spherical. The Sun pumps out the solar wind in all directions, pressure equalizes, you get a bubble. That's the intuitive picture. It was also probably wrong, or at least significantly incomplete. The Sun isn't stationary. It's moving through the interstellar medium at about 43,000 miles per hour relative to the surrounding gas and dust. When something moves through a fluid, it doesn't stay spherical. It compresses at the front and stretches at the back. Think of a comet and its tail, or a boat pushing a wake behind it. The heliosphere, according to a competing set of models, should look something like that, compressed on the side facing the direction of the Sun's travel, extended into a long tail on the opposite side, sometimes called the heliotail. That debate hasn't been resolved, and the Voyager data has actually made it harder to settle, not easier. Here's why. The two probes exited through roughly opposite flanks of the heliosphere. That sounds ideal until you realize the timing mismatch complicates the comparison. The heliosphere expands and contracts over the solar cycle, roughly an 11-year cycle of solar activity that changes how much energy the Sun pumps outward. When Voyager 1 crossed in 2012, solar activity was near a maximum. When Voyager 2 crossed in 2018, conditions were different. So the two crossing distances, 100 to 22 astronomical units versus 119 astronomical units, can't simply be compared as if they're measuring the same static object. You're taking two snapshots of something that's constantly breathing in and out. The density gradient data adds another layer. Voyager 1 has been detecting a steady increase in plasma electron density as it moves deeper into the very local interstellar medium. That gradient isn't uniform in all directions. The data implies there's genuine large-scale structure out there. The interstellar medium surrounding our solar system isn't a smooth, featureless ocean. It has currents, concentrations, regions of higher and lower density. That matters because the shape of the heliosphere is determined partly by the pressure balance between the solar wind pushing outward and the interstellar medium pushing back. If the interstellar medium has structure, the heliosphere responds to it. The boundary isn't just a product of what the Sun is doing, it's also a product of what the neighborhood looks like. The neighborhood is more complicated than the early models assumed. There's also the hydrogen wall. Both Voyager spacecraft detected evidence of a concentration of neutral hydrogen at the outer edges of the solar system. First noticed in 1992 and confirmed by New Horizons data in 2018, this wall forms where the solar wind starts interacting with the interstellar medium, piling up neutral hydrogen atoms that slow down and accumulate. The shape of that wall, exactly where it sits, tells you something about how the heliosphere is oriented and how it's interacting with the flow of the interstellar medium. But you need more than two crossing points to map it properly. So what would actually answer the question? A purpose-built interstellar probe sent in a different direction entirely could give you a third data point. Cross the heliopause near the heliotail, the stretched-out region trailing behind the Sun's motion. and you'd learn whether the crossing distance there is significantly larger than 120 astronomical units. That is what the comet tail models predict. Some estimates put the heliotail at several hundred astronomical units or more. If a probe crossed at, say, 300 astronomical units in that direction, you'd have your answer. The heliosphere would be dramatically elongated, not spherical at all. The proposed interstellar probe concepts that have been studied at places like Johns Hopkins Applied Physics Laboratory are partly motivated by exactly this question. A trajectory aimed at the heliotail, combined with instruments actually designed for interstellar science rather than planetary science, could map the heliosphere's shape in a way the Voyagers were never equipped to do. You'd get plasma measurements, magnetic field data, cosmic ray counts, all along a vector that neither Voyager touched. The problem is that any such probe is decades away from being funded, built, launched, let alone from reaching the heliopause. The Voyagers took about 35 years to get there. A faster mission could do it in 15 to 20 years with the right propulsion and trajectory, but that still means the data comes back sometime in the 2050s at the earliest, assuming a launch in the next decade, which is not guaranteed. In the meantime, scientists are doing what they can with what exists. NASA's IBEX spacecraft and the more recent IMAP mission are designed to map the heliosphere from the inside, using energetic neutral atoms that stream in from the boundary and carry information about conditions at the edge. IBEX data has already generated significant debate. Early maps suggested the heliotail was more structured than expected, with distinct lobes rather than a smooth trailing extension. Those findings haven't resolved the shape question either. They've sharpened it. What the Voyager data makes clear is that the heliosphere is a dynamic, asymmetric structure responding to two things simultaneously: the sun's own output and the environment it's moving through. Neither of those things is simple. Neither of them is static. And the region where they interact is leaky, magnetically complex, variable in ways that two spacecraft passing through it at 2 points in time can only partially illuminate. With only 2 data points, one on each side of the heliosphere, the complete picture of what our solar system's protective bubble actually looks like remains an open question. Strapped to the side of each Voyager spacecraft is a 12-inch gold-plated copper disc that was never meant to be heard by anyone currently alive. That's not a figure of speech. The records were designed with an audience in mind that doesn't exist yet, and may never exist. They were an act of hope aimed at timescales that are genuinely difficult for the human brain to process. When Carl Sagan and his colleagues put the golden records together in 1977, they weren't thinking in years or decades. They were thinking in billions of years. The spacecraft will outlast every building on Earth. They'll outlast the continents. In all likelihood, they'll still be drifting through the galaxy long after the sun has expanded and consumed the inner solar system entirely. The records were made for whoever or whatever might find them in that almost incomprehensible expanse of future time. Sagan was the driving force behind the project. He'd already thought seriously about what it might mean to send a message into deep space. When NASA extended the Voyager mission beyond its original planetary targets, he pushed for something more than just engineering. He assembled a small committee. They had roughly 6 weeks to decide what to put on a record that might represent the entirety of human civilization. Think about that for a second. 6 weeks. One disc. Every language, every art form, every sound, every image that might convey something meaningful about what it was like to be human on Earth in 1977. What they settled on is remarkable. Each record encodes 115 images, photographs of the sun, the planets, human anatomy, architecture, people eating, people running, a nursing mother, a highway at night, a supermarket. The idea was to give some sense of the physical world and the creatures living in it, without assuming anything about how the finder might perceive or interpret visual information. There are natural sounds: thunder, wind, surf, rain, the calls of birds and whales and frogs. There are greetings recorded in 55 different languages, ranging from Akkadian, an ancient Semitic language spoken thousands of years ago, to modern Mandarin. There's a greeting from a child. There's a message from Kurt Waldheim, who was the UN Secretary General at the time. And there is music. The music section is where the record gets genuinely strange and wonderful. Bach appears 3 times, the Brandenburg Concerto number. 2, the Prelude and Fugue in C, a partita for solo violin. There's Beethoven, there's Mozart, there's a Javanese gamelan piece and a Peruvian wedding song and a Pygmy Girl's initiation song from Zaire. And then there's Johnny Be Good by Chuck Berry. That means that somewhere beyond the heliopause, hurtling through the interstellar medium at 38.000 miles per hour, is a spacecraft carrying one of the defining songs of early rock and roll. Sagan was asked about this choice and reportedly said that teenagers all over the world danced to it. He wasn't wrong. The record also includes a diagram, a kind of map, encoded in the disk itself. That shows the location of Earth relative to 14 pulsars. Pulsars are rotating neutron stars that emit radio pulses at extremely precise frequencies. Those frequencies change in predictable ways over time. The map is designed so that any civilization capable of detecting and reading it could, in principle, triangulate our position in the galaxy and even determine when the record was made, using pulsar timing as a clock. It's an extraordinarily clever solution to a genuinely hard problem. How do you tell someone where you are without assuming they share any of your reference points? The record itself is built to last. It's gold-plated copper, which is highly resistant to corrosion. It comes with a cartridge and a needle. The cover includes instructions, encoded in diagrams, for how to play it. Scientists estimated that in the low-density, low-radiation environment of interstellar space, the physical record could remain intact for more than 1 billion years. The information on it could survive longer than that. Whatever gets pressed into that disk is, for practical purposes, permanent on any timescale that matters. Here's what's worth sitting with for a moment. Every other artifact of human civilization is temporary. The pyramids at Giza are eroding. The Library of Congress will not outlast the sun. Every book ever printed, every building ever constructed, every painting and sculpture and piece of recorded music stored on any medium on Earth, all of it is subject to the eventual decay of the planet that houses it. The Voyager records are not. They're in the void now, moving away from the sun at a speed that nothing we've built since has matched. In about 40,000 years, Voyager 1 will make a relatively close approach to a star in the constellation Camelopardalis. In the billions of years after that, both spacecraft will drift through the Milky Way essentially indefinitely, carrying their cargo of images and sounds and music and greetings long after any memory of them on Earth has vanished. That's the dimension of the golden records that tends to get lost when people talk about them. They're often described as a symbol of human aspiration or a message to the cosmos. Both of those things are true, but they're also the most durable objects the human species has ever produced. Not durable in the sense of sturdy or well-engineered, though they are those things. Durable in the sense that nothing else we've made will last as long, survive as much, or travel as far. There's something quietly staggering about that. The most durable thing humanity has ever made isn't a monument or a building or a book. It's a gold-plated record drifting through interstellar space at 38,000 miles per hour, carrying Chuck Berry and Whale Song and a map back to Earth. Before Voyager, the outer solar system was mostly a series of theoretical models, educated guesses about what might be out there, based on observations made through telescopes from billions of miles away. Scientists had math, they had orbital mechanics, they had spectroscopic data and theoretical predictions about what gas giants might look like up close. What they didn't have was any direct evidence. The difference between what they assumed and what Voyager actually found turned out to be enormous. Take the outer planets themselves. Before the flybys, Jupiter was a swirling gas giant with a big red spot. After Voyager, it was a system with active volcanic moons, intricate magnetic structures, a radiation environment so intense it nearly fried the spacecraft's instruments. Saturn's rings, which looked relatively clean and organized through Earth-based telescopes, turned out to be a chaotic, layered system with embedded moons and structures nobody had predicted. Uranus was tilted almost completely on its side, the result of a catastrophic ancient collision that had essentially knocked the planet over. Neptune had winds faster than anything else in the solar system. Every single encounter produced surprises, not minor surprises, fundamental ones, the kind that forced scientists to go back and rethink the basic assumptions behind their models. That pattern matters. It's not just that Voyager found interesting things. It's that the gap between theory and reality was so consistently large, across so many different objects, that it changed how planetary scientists approach their work. You can't look at the Io discovery, or the Shepherd moon problem at Saturn, or Triton's nitrogen geysers. Come away thinking that theoretical models alone are enough. Voyager made the case, as directly as any mission ever has, that you have to go there. You have to send something, and you have to measure it directly. This was because the universe is under no obligation to match your predictions. Then there's the heliosphere. Before Voyager, scientists understood in a theoretical sense that the sun's influence had to end somewhere. The solar wind couldn't blow outward forever. There had to be a boundary where it ran out of momentum, where interstellar space began. But nobody had ever measured that boundary. Nobody had ever been there. Voyager 1 crossed it in 2012. What it found confirmed something that has real consequences for every living thing on Earth. The heliosphere isn't just an interesting feature of the solar system. It's a radiation shield. It deflects galactic cosmic rays, high-energy particles produced by supernovae and other violent events across the galaxy, before they can reach the inner planets. Beyond the heliopause, cosmic ray intensity jumps dramatically. Inside it, we're protected. Think about what that means. The fact that Earth is habitable isn't just about distance from the sun or the presence of liquid water or plate tectonics. It's also about this vast invisible bubble surrounding the entire solar system, blocking radiation that would otherwise make conditions here significantly more hostile. Voyager gave us the first direct measurements confirming that the bubble is real and that it's doing something important. The pale blue dot photograph sits in a different category. It's not a scientific data point in the traditional sense. Voyager 1 took that image on February 14, 1990, about 3.7 billion miles from Earth, as part of a portrait of the solar system requested by Carl Sagan. Earth shows up as a fraction of a pixel, barely distinguishable from the background, caught in a scattered ray of sunlight. Sagan wrote about it in terms that have been quoted ever since. Every person who ever lived, every empire, every catastrophe and triumph, all of it playing out on a mote of dust suspended in a sunbeam. What the photograph did, in a way that no amount of scientific explanation could fully replicate, was make the scale visceral. You can be told that Earth is a small planet in an unremarkable corner of the galaxy. That's an abstract fact. Seeing it as a pale blue dot surrounded by the vastness of the outer solar system makes it something else entirely. It reframes the perspective in a way that sticks, and the scientific impact of the mission hasn't stopped. That's one of the stranger and more remarkable things about Voyager. Researchers today are still going back through data collected during flybys that happened 40 years ago, running it through modern analytical software, finding things nobody caught at the time. In 2023 and 2024, scientists re-examining archived Voyager, two data from the 1986 Uranus flyby, found possible evidence of an undetected moon and new clues about the planet's unusual magnetosphere. Those discoveries were made using instruments that didn't exist when the data was collected. The raw measurements were always there, stored and waiting. The tools needed to fully interpret them took decades to develop. That's not unique to Voyager, but Voyager is one of the most striking examples of it. A spacecraft flies past a planet at tens of thousands of miles per hour, spending a few hours in close range. The data it collects turns out to contain more information than anyone could fully process at the time. Decades later, with better computational tools and a clearer understanding of what questions to ask, scientists crack open those old files and find something new. The data doesn't age. The physics that produced it doesn't change. What changes is our ability to read it. There's also the simple fact that Voyager expanded the known solar system in a way that hasn't been matched since. Before 1979, nobody had seen a volcanic eruption on another world. Before 1980, nobody had a close-up of Saturn's rings. Before 1986, nobody had seen Uranus at close range. Before 1989, Neptune was an unresolved disk. Voyager turned all of those from theoretical objects into real, complex, measurable places, each one stranger than expected, each one demonstrating that the solar system is a far more dynamic environment than the pre-Voyager textbooks described. 47 years after launch, scientists are still pulling discoveries out of data that was collected during a flyby that lasted a few hours. That is about as good an argument as you can make for the value of a mission. Voyager's instruments were designed to study planets, not interstellar space. That means humanity's first two probes in the interstellar medium are carrying equipment that was never optimized for the job. The magnetometers, the plasma wave instruments, the cosmic ray detectors, they were all built with Jupiter and Saturn in mind. The fact that they've returned useful interstellar data is remarkable, but it's also a limitation that scientists have been thinking about for years. There's now a serious conversation underway about what comes next. The core problem is straightforward. Voyager 1 and Voyager 2 crossed the heliopause at 2 points on roughly the same side of the solar system, separated by a few degrees of trajectory. That gives you 2 data points. 2. To understand the full 3-dimensional structure of the heliosphere, whether it's roughly spherical, elongated like a comet tail or something more irregular, you need measurements from multiple directions. You need a probe heading in a completely different direction, carrying instruments specifically designed for the interstellar environment. You need it to get there faster than Voyager did. Voyager took about 35 years to reach the heliopause. That's not a timeline most funding agencies are enthusiastic about. Scientists and engineers at JPL and at the Johns Hopkins Applied Physics Laboratory have been studying what a dedicated interstellar probe might look like for more than 2 decades. The concept that's received the most serious attention is simply called the interstellar probe. The version studied most extensively would be a spacecraft launched on a trajectory carrying it to somewhere between 200 and 400 astronomical units from the Sun, well beyond where either Voyager is now, within roughly 50 years of launch. To do that, it would need to use a Jupiter gravity assist combined with a close solar flyby to build up enough speed. At its peak, it could be traveling at around 7 astronomical units per year. That's roughly twice Voyager's current pace. Here's what makes this genuinely different from just building another Voyager. The instruments would be designed from the start for interstellar science. A plasma spectrometer capable of measuring the full distribution of particle energies in the very local interstellar medium. A dust detector. A neutral atom imager capable of mapping the entire heliosphere from the outside, something neither Voyager can do. This was because you can't photograph a room you're standing inside. That last instrument is particularly significant. The only complete images of the heliosphere we currently have come from IBEX, the Interstellar Boundary Explorer. That maps neutral atoms from Earth orbit. Those maps are useful but limited. A probe actually outside the heliosphere looking back could map the whole structure in a way that's simply not possible from inside. The scientific questions a dedicated mission would address go well beyond just mapping the heliosphere's shape. The hydrogen wall, a concentration of neutral hydrogen that piles up at the outer boundary between the solar wind and the interstellar medium, was first detected in 1992 by the Voyagers themselves, but never directly sampled. A purpose-built probe could fly through it with instruments calibrated specifically for that measurement. The structure of the very local interstellar medium is another open question. Voyager 1 has been detecting a density gradient as it moves deeper into interstellar space, suggesting there's real structure out there. Not a uniform medium, but a region with variation that hasn't been mapped. 2 data points from 2 aging spacecraft can't tell you what that structure looks like at any scale. You'd need a probe that could take systematic measurements over a range of distances and angles. There's also the question of cosmic ray composition and energy distribution beyond the heliopause. Voyager's cosmic ray instruments have provided a decade's worth of data on that, but they weren't built to resolve the full spectrum of particle energies with the precision that modern detectors can achieve. What's arriving from the galaxy and the space between stars? At what energies? From what directions? A next-generation probe could answer those questions with a level of detail the Voyager simply can't provide. So why hasn't this mission been funded yet? The short answer is that it's expensive and it takes a long time to pay off. A mission to 200 astronomical units, even at twice Voyager's speed, takes decades to return its primary science. The scientists who propose it will mostly not be alive when it arrives. The engineers who build it will be working on a spacecraft that won't be heard from again in any meaningful sense until their careers are long over. That's a difficult argument to make to a funding committee trying to allocate resources across dozens of competing priorities with shorter return horizons. The interstellar probe concept was studied extensively in NASA's 2023 to 2032 Planetary Science Decadal Survey. It received serious consideration. The decadal survey process is where the scientific community collectively argues about what missions matter most over the next decade. The fact that an interstellar probe made it into that conversation at all tells you the scientific case is there, but it wasn't selected as a flagship priority. The funding competition is brutal, and the timeline is brutal. Flagship missions cost billions. There are missions to Europa and Uranus competing for the same limited pool of money. Those missions return their primary science in years, not generations. That said, the concept hasn't gone away. Researchers at Johns Hopkins have continued refining the trajectory options and instrument packages. There are newer proposals that would take advantage of advances in low-mass instrument technology to reduce the overall mass of the spacecraft and therefore the cost of reaching high speeds. The closer solar flyby required for maximum speed pushes the engineering limits of thermal protection, but those limits have been pushed before. The Parker Solar Probe has gone far closer to the Sun than anything before it. Any successor mission to Voyager would take decades from approval to arrival at the heliopause, and that assumes it gets funded at all. That is never a safe assumption for a project with a price tag in the billions and a science return measured in human generations. There is a small team of engineers and scientists at NASA's Jet Propulsion Laboratory who have spent decades of their professional lives listening to signals from Voyager 1. Some of them have been doing it since the spacecraft launched. That's not a metaphor. These are people who were in their 20s and 30s in 1977, who spent their careers tracking a machine moving away from Earth at 38,000 miles per hour, who are now in their 70s and 80s. Some of them have died. The spacecraft is still transmitting. Think about what that means for a moment. The standard model of exploration involves the explorer returning. Magellan's crew came back. The Apollo astronauts came back. Even the unmanned probes to Mars eventually go silent after a few years, and the teams move on. Voyager doesn't work like that. It's been leaving for 47 years. The people who built it have had to live with the knowledge that it will keep going long after all of them are gone. The mission doesn't have an ending. It just has a point where the signal finally becomes too faint to detect. That's genuinely different from anything in the previous history of human exploration. You can draw the analogy to the great maritime expeditions, to Cook, to Magellan, to the ships that mapped the Pacific coastlines, but the analogy only goes so far. Those expeditions were measured in months or years. The explorers were human beings who could report back what they'd seen, who could describe the experience of being somewhere new. Voyager's crew, if you can call it that, consists of instruments, plasma wave sensors, magnetometers, charged particle detectors. They can tell you the electron density of the interstellar medium, but they can't tell you what it's like to be there. That gap is worth sitting with. There's something else that separates this kind of exploration from everything that came before it. When Lewis and Clark reached the Pacific, they knew they'd gotten there. When Amundsen reached the South Pole, he planted a flag. The arrival was immediate and legible. When Voyager 1 crossed the heliopause in 2012, nobody knew for sure what had happened for almost a year. The data had to be analyzed, debated, reanalyzed. Scientists argued about what the instruments were actually measuring. The moment of crossing didn't feel like a moment at all. It felt like a slow accumulation of evidence that eventually became undeniable. Exploration at this scale doesn't come with a clear signal that you've arrived, and yet the emotional investment is real. Ask anyone who's worked on the Voyager mission for a significant stretch of time, and you get something that sounds less like professional detachment and more like a long relationship with a machine. Ed Stone, who served as the project scientist for Voyager for more than 4 decades, described watching the heliopause crossing as one of the most significant moments of his career. He was a young physicist when the spacecraft launched. He was in his 80s when Voyager 2 made its crossing in 2018. There aren't many professions where your most important work spans half a century and is still ongoing after you've retired. What's strange about Voyager's place in the history of exploration is that nothing has come close to matching it since. You might expect that 47 years of technological progress would have produced something faster, something more capable, something that has already surpassed the Voyagers in distance from Earth. It hasn't. The New Horizons spacecraft, launched in 2006 and far more technologically sophisticated than either Voyager probe, is moving outward at about 36,000 miles per hour, slower than Voyager 1's 38,000. It has covered roughly 60 astronomical units from the Sun. Voyager 1 is past 165 astronomical units. The gap isn't closing, it's growing. Part of why Voyager got so far so fast comes back to that 176-year planetary alignment. The gravity assists from Jupiter and Saturn flung both probes outward with an efficiency that a direct launch could never replicate. You can't just decide to repeat that sequence. The geometry doesn't cooperate again for more than a century. Any future probe heading for interstellar space will need to find a different path. Most of the proposed trajectories involve decades of travel just to reach the heliopause, let alone the very local interstellar medium that Voyager is crossing now. So what you have is this: two spacecraft built with 1970s technology, designed for a 5-year mission, carrying instruments that were never intended for interstellar science. That happened to be the most distant human-made objects in existence and are likely to remain so for the rest of your lifetime. The scientists who built them are gone or going. The engineers who keep them running are doing so with an ever-shrinking power budget and increasingly rare institutional knowledge of systems that nobody else in the world fully understands anymore. And every day the signal gets a little weaker and the one-way travel time for a radio transmission gets a little longer. There's something in that situation that resists easy summary. It's not triumph exactly, though it is that. It's not tragedy, though there's loss woven through it. It's closer to what happens when a thing you made outlasts your ability to fully understand what it's doing and why it matters. And it keeps going anyway, indifferent to whether you're watching. Voyager 1 and 2 remain nearly half a century after launch, the farthest objects from Earth that human hands ever built, and nothing currently in development is on course to overtake them anytime soon. Put together everything the two Voyager probes have measured since crossing the heliopause, you get the first genuine portrait of interstellar space drawn from direct observation rather than theoretical inference. And what that portrait looks like is not what most people would expect. Before either spacecraft crossed the heliopause, scientists had models. Reasonably detailed models built on decades of theoretical work and indirect observation. Those models got some things right, they got others significantly wrong. And the gap between what was predicted and what Voyager actually measured is where most of the interesting science lives. Start with the plasma. Inside the heliosphere, the solar wind fills space with a relatively thin, fast-moving stream of charged particles, hot, low density, constantly pushed outward by the sun. The expectation was that interstellar space on the other side would be denser, colder, and calmer. That part was correct. What the instruments found is that the plasma in the very local interstellar medium is roughly 80 times denser than the plasma inside the heliosphere. That 80-fold jump was actually the key measurement that confirmed Voyager 1 had genuinely crossed the heliopause. Scientists detected plasma oscillations in the spring of 2013, caused by a solar outburst that had traveled outward and disturbed the local plasma. The frequency of those oscillations told them the electron density of the surrounding medium, and the number came back 80 times higher than what Voyager had been moving through before. That was the eureka moment. Not a dramatic alarm, not a flashing light. A frequency, a number that was just too high to be anything other than interstellar space. But here's where things get strange. The temperature at the heliopause boundary itself is extraordinary. Measurements suggest somewhere between 30,000 and 50,000 Kelvin, tens of thousands of degrees. That's hotter than the surface of many stars. If you told someone the edge of the solar system registers at 50,000 Kelvin, they'd assume anything passing through it would be instantly destroyed. But Voyager wasn't, because temperature in a near vacuum doesn't work the way temperature works in your kitchen. Temperature is a measure of how fast individual particles are moving. Out there, the particles are moving incredibly fast. There are just almost none of them. The density is so low that even though individual particles carry enormous energy, there aren't enough of them colliding with anything to transfer significant heat. You'd pass through that region and barely feel it. It's one of the most counterintuitive things the mission produced, a region that reads as scorching hot on the instruments, but would feel like nothing. Beyond the heliopause, the cosmic ray environment shifts dramatically. Inside the heliosphere, the sun's magnetic bubble deflects a significant fraction of the high-energy particles that flood the galaxy, particles produced by supernova explosions and other violent events far across the Milky Way. When Voyager 1 crossed the heliopause, the instruments recorded a roughly 9% jump in fast-moving galactic cosmic rays almost immediately. That number has kept climbing as Voyager moves deeper into the interstellar medium. Think about what that means for any future mission carrying humans beyond the heliopause. The radiation environment out there is measurably significantly more hostile. The heliosphere isn't just a theoretical construct, it's doing a real, quantifiable job of keeping the inner solar system safer than it would otherwise be. The magnetic field environment also turned out to be more complicated than the models predicted. The solar magnetic field drapes around the heliopause rather than cutting off cleanly. Outside, the interstellar magnetic field runs at a different orientation than expected. The boundary isn't a sharp line so much as a zone of interaction, with field lines bending and compressing and creating structures that don't fit neatly into the pre-Voyager picture. In 2020, Voyager 1 recorded a distinct jump in magnetic field strength at about 149 astronomical units, followed by what scientists describe as a persistent hump, a region of elevated field strength that has continued as the spacecraft moves outward. Nobody has a complete explanation for it yet. It's just there in the data, waiting. Then there's the hum. In late 2020, Voyager 1's plasma wave instrument detected something that researchers described as a persistent narrow-band oscillation in the surrounding plasma. Not a one-time event triggered by a solar outburst, a continuous signal. Interstellar plasma vibrating at a consistent frequency, essentially humming in the dark. It had almost certainly been going on long before Voyager arrived to detect it. The instrument just needed to be in the right place to pick it up. Scientists also found that the electron density has been rising gradually as Voyager 1 travels deeper, not in random bursts, but as a large-scale gradient suggesting the very local interstellar medium has structure and organization that extends across enormous distances. The interstellar medium isn't uniform. It has topology. It has regions. What's striking about all of this is what it isn't. It isn't the violent, dramatic chaos that science fiction tends to imagine beyond the edge of the solar system. There are no crackling energy fields, no visible turbulence, no clear demarcation you could watch yourself cross. What the instruments found is something more unsettling in its own way, an almost incomprehensible emptiness, crossed by faint magnetic structures and populated by particles so sparse they barely interact with anything, all of it vibrating at frequencies too low and too slow for any human sense to register. The plasma hum carries on whether or not anything is there to detect it. The cosmic rays stream through whether or not anyone is counting them. The magnetic field drapes and compresses according to physics that operated long before the sun formed. Voyager didn't find a frontier. It found a medium that was there all along, indifferent and vast. And the mission opened as many questions as it answered. The shape of the heliosphere is still genuinely uncertain. The mechanism behind the magnetic hump at 149 astronomical units is still unresolved. The large-scale density gradient Voyager 1 is moving through still doesn't have a fully accepted explanation. Scientists are still working through data from the 1986 Uranus flyby and finding things nobody noticed the first time. That's what the mission actually looks like up close. Not a clean list of discoveries checked off one by one, but a decades-long accumulation of measurements that keep generating new problems to solve. Somewhere out there, about 15 billion miles beyond the edge of the sun's influence, and still moving outward at 38,000 miles per hour. A spacecraft built in the 1970s is humming along through the dark, measuring the plasma that fills the space between stars, sending the data home, one faint radio pulse at a time, taking more than 22 hours to arrive.